In this video, we are going to do a problem based on backpropagation. This is a sample figure for this problem. That is, this is a multi-layer perceptron which contains one hidden layer, the input layer, and its corresponding output layer. The input layer contains 3 neurons. The hidden layers contains 2 neurons, 4 and 5 respectively, and the output layer neuron is marked as neuron 6. The table 1 shows the initial input and the initial weight and bias values. Here, according to the question, the input is 101, that is, input is 3-dimensional, or we have 3 features in this architecture. And the corresponding class label for the input 101 is given as 1. This is the solution to the problem. Here you can see that this is the architecture given in the question, and this is the table given according to the question. Now we are going to calculate the net input and the output calculations, and table 3 represents the calculation of the error at each node. For calculation of net input and output, here this shows the equation for each hidden calculation of net input for each hidden layer or the output layer. The calculation of net input is given as by the equation Ij is equal to summation of I into Wij or Oi plus theta j. W are the weight and the theta j is the bias. Here for the neuron 4, that is, we are calculating the net input and output with respect to the neuron 4. That is, first we have to calculate the net input. After calculating the value of net input, using that we will be calculating the corresponding output. For the net input in the neuron 4, the equation is given as summation of I into Wij into Oi plus theta j. So the input parameters corresponding to neuron 4 is W14, W24 and W34. Here you can see that W14 is equal to 0.2, W24 it is equal to 0.4 and W34 is equal to minus 0.5. The corresponding input to this neuron, that is an input from the neurons 1, 2 and 3 is 101. That is given in the question. So to calculate the net input, you have to multiply the x1, that is 1, into W14, that is W14 is given as 0.2. So 1 into 0.2 plus the input value of x2, neuron x2 is 0. So 0 into W24 is 0.4, that is 0, plus 1 into W34 is nothing but minus 0.5. So it is 0.2 plus 0 plus minus 0.5 plus the bias. The bias is given as minus 0.4. Hence the expression is 0.2 plus 0 minus 0.5 minus 0.4. The resultant is minus 0.7. To calculate the output corresponding to the neuron 4, that is given by the equation Oj is equal to 1 by 1 plus e raised to minus Ij. Ij is the value which we have obtained here. So it is calculated as 1 by 1 plus e raised to minus of minus 0.7. It is equal to 0.332. So the output to this neuron from this neuron is 0.332. With the calculation of net input and output corresponding to the neuron 5. Here we have the equation. According to the equation, you can see that the weight vectors corresponding to the neuron 4 is represented as W15, W15, W25 and W35 respectively. So W15 is minus 0.3 and W25 is 0.1 and W 0.35, it is 0.2. And the input value as given in the question, it is 101. So minus 0.3 into 1 plus 0 into 0.1 plus 1 into 0.2 plus the bias quantity, that is bias quantity is 0.2. The resultant value of this expression is 0.1. To calculate the output, it is 1 by 1 plus e raised to minus 0.1, that is equal to 0.525. The similar calculation is performed with respect to the neuron 6. Like here you can see that the input is from input to this neuron 6 is from neuron 4 and 5 respectively, and the weight vectors are W46 and W56. So here you have the output from these neurons are calculated as 0.332 from neuron 4 and 0.525 from neuron 5. So using these output values, you can calculate the net input as W15 into 0.332. It is not W15, it is W46. W46 is 0.3 into 0.332 plus minus 0.2, that is W56 is minus 0.2 into 0.525 plus the bias, that is bias is theta 6 is equal to 0.1, and the resultant quantity is minus 0.101105. The output to this neuron is 1 by 1 plus e raised to 0.105, that is equal to 0.474. If we have calculated the output, the next step of the backpropagation algorithm is calculation of the error at each node. The error calculation, for the error calculation, we have to use two different expressions, that is for each unit in the output layer. We have to start the calculation of error from the the output layer back to the input layer. That is, we have to calculate the error first with respect to the neuron 6. After calculation of error with respect to neuron 6, we will be calculating neuron 4 and neuron 5. Yeah, the calculation with respect error with respect to output layer, or the expression with respect to the error in output layer, is different with respect to the hidden layers, neurons in the hidden layers, or errors in the hidden layers. So now let's look at the error with respect to the output layer. Error j is equal to oj into 1 minus oj into tj minus oj. Tj is nothing but the target given in the question. The target value or the output value is 1. So with respect to unit 6, the output OJ is calculated as 0.74. So 0.474 into 1 minus 0.474 into 1 minus 0.474. The resultant value is 0.1311. Now the error calculation with respect to unit 5 and 4. With respect to unit 5 and 4, these layers is there in the hidden layer. These neurons are in the hidden layer. So the expression for calculating the error is different. So it is equal to Oj into 1 minus Oj into summation of k into error k wjk. K is nothing but it represents the neurons or calculations with respect to the higher layer. So for 5 and 4, the next neuron in the next layer is neuron 6. So now let's look what is error with respect to neuron 5. So it is OJ. OJ for neuron 5, it is calculated as 0.525 into 1 minus 0.525 into error 0.1311. So the error with respect to the next layer, it is 0.1311, which is already calculated, into weight. Into weight is W46 and it is minus 0.2. Minus 0.2 it is given here. The resultant quantity is minus 0.0065. Similar calculation is done with respect to neuron 4. Once we have calculated, the third step in the propagation algorithm is weight updation. So we have to update the weight with respect to each connection in the architecture. So we'll start the calculation with respect to W46. Now, to calculate the weight with respect to W46, the equation is given here. Initially, we have to calculate the change in weight. Change in weight is nothing but L into error J into OI. Here you can see that learning rate is L is equal to 0.9. It is given in the question. So you can see that for error calculation at W46, this is the original weight which is given in the table. So it is given as W46 is given as minus 0.3. That is minus 0.3 plus learning rate 0.9 into error J, which is calculated in the previous slide. It is 0.1311 into OI. OI is nothing but 0.332, which is calculated and shown in the previous tables. That is equal to minus 0.261. Now calculation of W56. W56, that is the weight updation with respect to this link which connects the neuron 5 and 6 respectively. So that is nothing but the existing given weight plus the updated weight. So given weight for W56, it is minus 0.2 plus L into, that is 0.9 into the error. The error is calculated with respect to this link. This node it is 0.1311 and the output with this is 0.525, that is equal to 0.138. This equation can be represented, or these steps can be repeated for evaluation up till W35. Now let's look what is the error calculation with respect, weight update with respect to the bias quantity. Bias quantity is given as, change in bias quantity is given as L into error J. For calculation of theta J, it is L into error with respect to that neuron. So for theta 6, we have to sum the existing bias quantity, that is given as 0.1 over, zero point 0.1 plus zero point 0.9 is the learning rate into the error with respect to this node, that is calculated as 0.1311, and the resultant quantity is 0.218. This is the first step calculation of the parameters. And according to the question, we are asked only to calculate the first update. This updation can be done several times depending upon the epochs or the learning rate, accuracy. Or thank you.